Okay, so welcome everybody. This is part of the APS 2023 users meeting for our workshop entitled Fundamentals and Application of HEDM. So I guess with this, first let me introduce my co-organizers. I'll say that this has been really a team effort. June Singh Park is on the line here from APS, and I believe many of you know him. He'll be our next speaker, so I'll save the floor for him in a minute. Marm Dixit from Oak Ridge National Lab is one of our other co-organizers. He'll be joining in about an hour. He had an engagement that he couldn't get out of. And myself, Mike Sandridge from Purdue University. We were the three co-organizers, but we had a key advisor, Dr. John Ulmer, also from the Advanced Photon Source, was with us every step of the way. Great. So with this, our plans here is to really discuss high energy X-ray diffraction microscopy. And this is really enabled through 1ID and now with the upgrade 20ID. So I think it's a key time to bring people together. We, as co-organizers, we talked quite a bit about having a broad audience. So really making this inviting for folks that are potentially new users without the background of high energy X-ray diffraction microscopy. So we'll be discussing the fundamentals of the techniques, beamlines, even reconstruction software. And with that, start to go into the new beamline capabilities. As well, we wanted to make this interesting and exciting for expert users as well. So with that, we'll be talking about really advances to the state of the art. And these could be dynamic measurements going from typical grain average high energy X-ray diffraction microscopy results to subgrain measurements and complementary techniques for subgrain measurements. As well, we wanted to start to look towards the future. I mean, this is an exciting time at APS. As of a couple of weeks ago, the beam went down to have an upgrade. So we're going to take this as an opportunity to talk about new science opportunities and ideas for first experiments when the beamline comes back in about a year from now. So with all of this, well, maybe I can bring up the schedule and talk a little bit about how we put this together. Okay, can everybody see my screen? Great. So we're in the midst of just a introductions, which you guys will wrap up here shortly. And then June's going to talk about a overview of the techniques and beamlines at Argonne. So this will be a real insight into what Argonne has enabled us to do as the user communities, and also introduce for new users about this technique and technique and capabilities. We've heard last night that there's a good chance that Dr. Sharma, Hemant Sharma, is pulled away and won't be able to make it. So we'll do the best to fill the time, and I think June has some notes to go over about HEDM data analysis and reconstructions there. So that's really the first session meant to level set everybody about the fundamentals of HEDM. In our second session, we really want to focus on applications. So we've tried our best to make sure we're looking at diverse application sets. So Marm is going to talk about really battery materials. Chuan is going to talk about nuclear materials for nuclear structural applications. And then Paul Shade is going to be talking about aerospace materials. In the second session, I believe June is going to be our session chair. And with all of these talks, we're really targeting a total of 30-minute talks, but 20 minutes of presentations and really 10 minutes of Q&A. So hopefully this will have a lively discussion. We'll break for lunch, and then in session 3, which is going to be hosted by Marm, we're really going to focus on subgrain level measurements. So Henrik is going to be talking about diffraction tomography. Stefan is going to be talking about Bragg coherent diffraction imaging. And then Ashley is going to be talking about point focus HEDM capabilities. With all of this, we're going to get into our last section, or last of the third session, where John and I are going to lead a panel discussion, hopefully with all of you, about thoughts on first experiments and forward-looking science. Now, in the fourth session, chaired by June, we're going to start to look at advancements in application as we start to look into HEXM, so advancements with the synchrotron. So in terms of kind of zoom in type experiments, Sven is going to be discussing a combination of HEDM and dark field microscopy, allowing combinations of grain average across the full field view and sub-grain level information. Lian Li is going to be looking at dynamic experiments and really in situ additive manufacturing. And Antonian will be finally talking about utilizing real-time HEDM data to fine-tune and make decisions about subsequent experiments processing after that. So with that last talk, it's really utilizing some aspects of machine learning. So all of this is put together in such a way where we can start to bring together new users, look at experiences of existing users, and then really talk about what the future of HEDM is. So we're excited to bring this all together today and have a lively discussion. Let me pause there and ask June or John if they would like to add anything.
So June will be talking soon. I'll just mention, just as you're hearing these talks, think about, if you haven't already, some of the first experiments you might be interested in. And even if they're kind of wacky ideas, we don't mind hearing them a little bit, what one might call wacky, others call brilliant, in the kind of panel discussion. And I'll give a little bit of timeline as to experiments that we expect getting proposals in. Thanks.
Great. Thanks, John. So with that, let me hand it over to our co-organizer, Dr. June Park, who's going to be talking about an overview of the techniques in beamlines for HEDM.
All right. Thank you, Mike. Thanks, John. Let me set up my presentation here. Let me see. There we go. Can you guys see the presentation screen?
Yes, we can.
Fabulous. Put this back like this. Oh. Well, I guess I'll have to do this. Does that work? You guys can all see? Okay. I think if I go to presentation mode.
Yeah, go to presentation mode, June. I think if you then just do swap, go to the top display settings, swap presenter.
Let me see.
Top middle. Yeah. Swap.
Okay. How's that? Is that better?
Yeah.
Yes.
Okay. One trick I learned today. Good. Okay. I'm going to shut my video for now, and then I'll get going. Okay, well, thanks again for the introduction, Mike and John, and welcome everyone to the 2023 APS Users Meeting Workshop number 5. We're going to talk about some applications of high-energy diffraction microscopy. My name is Junsang Park, and I'm a beamline scientist with the Materials Physics and Engineering Group at the APS. I work primarily at Sector 1 and 1ID and 6BM. So the objective of the slide that I'm going to present today is to introduce several materials characterization techniques using high energy X-rays that has been developed at 1ID in collaboration with many users and expanding those programs. The basic idea is that we want to extract multi-dimensional attributes from voxels or sample points, and we want to also introduce here through the talk various characterization techniques and in situ sample environment portfolio that will be upcoming after APS-U. That'll be pushing the spatial and temporal resolution. We'll be talking about the beamlines that would be operating in the future. And like Mike mentioned, we have very exciting lineup of workshop speakers that I will highlight sort of to give them cues as to what they're going to talk about. And of course, we want some user feedback and about where we're going and discuss some of the first experiments or ideas that you might have about what to do with the new improved resolution after APS-U. So before I go into the main part of the talk, I'd like to acknowledge many people that's been involved in the developing these high energy diffraction microscopy techniques. And furthermore, the HEXM new beamline that's being built, the high energy X-ray microscope beamline. John Almer and Sarvjit Shastri, they've been co-lead scientists of this endeavor, the HEXM endeavor. And of course, our group members, particularly Aili Mashayeki, who makes a lot of things happen in the background. Very much appreciated. APS engineering has been particularly instrumental in developing new instrumentation that's pushing the limits of stability and structure stability and really meeting our needs. And of course, our collaborators, Himansh Sharma, for providing the working on MIDA suites, and Sinisha Viselli for his work with data management architecture and his team, and Nino Micheli in at APS detector pool that's been very helpful in selecting detectors and being very supportive of high energy programs. And then, of course, I'd like to thank you guys, the 1ID and 6PM user community that's been providing very valuable input and pushing us to the limit in many good ways. And of course, our funding agencies, particularly the DOE Office of Science, Basic Energy Sciences. So the main scientific driver for developing these high energy characterization probe is to understand the structure, property, and performance relationship in these hierarchical material systems. And that's going to, I believe, will come up in many multiple slides throughout the day. And you guys have probably seen some slides like this in the past. The idea is the material is made up of hierarchical structures ranging from atomic structure to nanostructure to single grain structures and grains, and then leading up eventually to the full assembly at many length scales, covering many length scales. So we've been developing these high energy techniques that can cover these length scales and really be sensitive to changes at the length scale so that we understand how materials behave at those length scales and how those changes affect the properties and performance of the structures eventually to the full assembly. One of the challenges is that we still have significant gaps in the measurement capabilities in the spatial and temporal resolution. So through the APS-U, we want to really bridge this length scale characterization gap that's highlighted here with these varying techniques, and particularly and also do these conventional measurements better. We also want to focus on keep doing multi-motion measurements, zoom in and zoom out, and also using different types of probes that are sensitive to different characteristics so that we get a more fuller picture of materials at different length scales. So before I go further with some description of different techniques, I will just introduce a generic or a common coordinate system that we will use throughout the talk and that we use throughout the talk. So we basically have monochromatic X-ray beam coming in. We have slits and X-ray optics that are often used to condition the beam to the size and sizes that we want. We have a sample and sample environment sitting here, and positioning stages that will move the sample appropriately. Of the sample positioning stages, the particular importance is the rotation. That's critical for getting multidimensional data, and I'll highlight that as I go along with the slides. Downstream end, because we're using a transmission geometry, we have an area detector downstream. We have a transmitted beam that's measuring the absorption or phase contrast information as information of the beam induced by the sample. And also we have the scattered beam measured by the area detector. Sometimes you can put a what is called a diffractive beam aperture to isolate a particular volume in the sample. And this is a schematic of the 1ID beam, 1IDE enclosure, experimental enclosure that really realizes this geometry and takes advantage of this geometry, where we have the X-ray beam coming in from the right. We have various sample manipulation stages, or focusing on slits here. And we have the sample manipulation stage or positioning stages and in situ environments. And then various detectors along the beam measuring different things about the sample. So our material characterization technique using high energy X-rays, I would call it a multimodal tomography, in the sense that in the direct beam, we measure the absorption or phase contrast induced by the sample. Or we look at the scattered or diffracted beam, and depending on what the grain size is with respect to grain size to the sample with respect to the spot size, I would call one a scattering using scattering tomography or high energy diffraction microscopy. In the case where the grain size is small relative to the spot size, or grain size is similar to the spot size. Bottom line is that because we're looking at scattering phenomena, we're looking at multiple attributes such as strain, orientation, dislocation, density, whatnot. And we typically combine all these measurements so that we have a fuller picture of the sample with different attributes. And of course, we include in situ in a sample environment because we want to track how the sample is changing with applied stimulus and understand how things, understand their behavior, material behavior. So existing techniques, we mainly focus on sample rotation translation. This has two effects. One has, it enlarges the effective field of view, and I'll get to that, and that'll be a common thing that I'll talk about throughout the talk. And also, we'll be able to interrogate higher dimensional and improved resolution maps through reconstruction algorithms. And then, of course, the new techniques that are coming up in the horizon, as with the APS-U, we will try to close the characterization length gap by deploying measurement techniques that can really take advantage of the spatial, the APS-U coherence to attain higher spatial resolution in the length scale of nanometers, tens of nanometers, and also temporal resolution with exploiting increased flux, and also new technologies that can deliver a higher frame rate, higher frame rates. So what I mean by, let's go into some techniques in detail. So in the direct beam, we can talk about tomography / radiography and transmission X-ray microscope. If you're talking about single projection with no sample translation in X and Y, this is one field of view radiography. This is commonly, if you've been to the beamline, this will be what we use to basically align the sample or take snapshot of the sample at specific points that are interesting. Now, if you were to take single projections of this field of view, which is typically about 2 by 1 millimeter, and then translate the sample in XY with respect to the beam. So in this case, it's a compact tension sample where the crack was growing and bifurcating and whatnot. This is a 13 millimeter crack. And if you can translate the sample with respect to the beam and make a montage, it's basically a stitching radiography. Now, if you start to do multiple projections of the sample while the sample is rotating, particularly using this geometry here, where you have the incoming beam, the sample sits right in that location, and you rotate the sample using this theta y prime, and you take this multiple projections like this, and you deploy some smart reconstruction algorithm, you can now start to get a 3D picture of what's going on in your sample. So in this case, what we're looking at is a copper tin niobium wires. We take projections of it using very high energies. I think in this case was 90 kV plus. And we do the reconstruction, and you can get the 3D structure. This is a slice of this wire, but you can get the 3D structure of this wire bundles that are very unique, and they understand how they're formed and how they change with heating as we heat these things. This was a measurement that one of our users did from Lawrence Berkeley lab. Of course, you can also do multiple projections during rotation, and then you can translate the rotation axes. And this enables what is called stitching tomography, where if you have samples that are larger than the single field of view, you can stitch many projections together and interrogate and get a 3D picture of samples that are larger than your field of view. So this is really something that's been coming along nicely that enables us to look at bigger samples. These measurements right now and in the future will be sort of limited to about a micron type of spatial resolution. If you want to go sub-micron into the nanometers range, Sarvjit Peter and Bob Suter at Carnegie Mellon has demonstrated that in high energy regime, transmission X-ray microscope is possible, this TXM technique, which will get us to a sub-micron resolution. This is done by, instead of just on top of this conventional geometry, adding a magnifying optics to magnify the real space image and imaging it on a detector downstream. And this will be coming along and as part of the program at the new beamline that we're developing at 20ID, the HEXM beamline. So now, if we start to get into when we start to look at scattering and using that as a contrast mechanism to study materials, I'll start off with saying that while we advertise this session as a high energy diffraction microscopy session, and typically HEDM is associated with getting individual grain information, I would like to expand that definition a little bit to include basically microscopy that uses high energy X-rays to look at materials of grains with variety of sizes. So in this case, we're looking at samples that have grains or scattering volumes that are very smaller than the spot size that we're deploying, the X-ray spot size. So typically, we're talking about something like a small angle X-ray scattering or wide angle X-ray scattering here, where we have a sample, we have an incoming X-ray, and this is the spot size, the yellow line here, and anything that satisfies the diffraction condition along this beam is collected on a Sachs wax detector, as shown here. And then, depending on which direction you're looking for or looking at, you can extract a lot of information from this 2D pattern. For example, if you're looking at peak position, you're looking at some directional strain. If you're looking at peak intensities, you can start to talk about preferred orientation of this crystal or organization. Or peak width, start to talk about dislocation arrangements and plasticity. And of course, like I alluded before, if you start to translate and rotate, you get higher dimensional spatial maps and also directional attributes, and also filling in the pole figure, so to speak. And of course, in some cases, the samples can be larger in X and Y, because if you're trying to make a simple 2D map, you can simply translate. Sample sizes are typically limited in Z by attenuation. Okay. So similar to the direct beam tomography case, if you start to translate your sample, if you don't do any translation at all, then you're just basically looking at a single point while you're summing up all the grains in the beam path. What is going on at that single point? And if you sort of assume that a point in your sample is representative volume element as other points in the sample, then you can just keep doing the same measurement at the single point while you, for example, load your sample with thermo-mechanical loading and capture the diffraction or scattering data on the wax detector or the SAX detector. And then see, for instance, as you apply some load on your sample, as highlighted by a stress strain curve here, how do the strains in the loading direction and the transverse direction, if your sample is being loaded this way in the Y, how do the transverse and the loading direction strains change with applied load, right? So you just look at one point and then you keep measuring and you look at the strains and see if they break from linearity, not break from linearity, what are the inflection points, et cetera, et cetera. Now you can build on that idea and then you can do 1D or 2D translations in the X and Y, so perpendicular to the beam. And you can now start to get a map. In this case, it's a line on the sample. So in this case, a compact tension sample was pulled to grow the crack, and this user wanted to study how crack propagation, as the crack is propagating in a hydrogen environment, how does the strain distribution and dislocation density distribution change in the crack front? So you can make a 2D map by translating the sample in X and Y, or in this case, what they did was simply move along the crack front and then measure the dislocation density and the strain in the loading direction. Okay, and you can learn a lot from these type of measurements and answer questions that are outlying in terms of how these material systems behave in these complex structures. Now, one offshoot of this type of 0D measurements, a single point measurement, would be doing these measurements really fast. So I will highlight that this is something that Andrew Chuang in our group and has been leading this effort quite a bit, combining, for example, dynamic processes like additive manufacturing and deploying a very fast, very high frame rate diffraction detector and also imaging detector to image both in diffraction and in radiography how the powder bed changes and how solidification happens. Okay, so unfortunately the video is not available here, but we can wait for perhaps Dr. Chen's talk later today, and he might have some beautiful videos of how this phenomena happens and how we really use high energy X-rays to characterize these type of systems, going from amorphous state when it's liquid to solidifies, how that phase diagram looks like and how it's different depending on how the rate and the power that's inputted into the powder bed. So that this type of information, of course, is very important for guiding the development of kinetics-driven synthesis routes of these very complex alloys and structures. Oh, now it works. All right, so the two videos work now, and on the left here is the scattering information at a spot, and you can see that material goes from some amorphous phase in the liquid phase to some solidification with various diffraction peaks forming. And that's a piece of information you can get. And on the right here, it's a radiograph indicating a field of view looking at the powder bed as a laser is going through across. And you can see that the laser is going through and inserting various structures that are very interesting as things solidify. Now, let me see. Of course, in the translation cases that I've mentioned earlier, I've mentioned that we are summing everything along the beam path, but now there are some ways in which you can actually measure depth resolved. You can actually conduct depth resolved measurements. One way is a method is to place a diffracted beam aperture downstream of the beam of the experimental geometry, and selectively choose only a volume scattering from a particular volume to go through and land on and be detected on the detector. The other method is a method on the right here that uses energy dispersive diffraction to also isolate a volume in your sample, subsurface volume in the material, and study material that way. So on the left here, this is a case where if you had a diffracted beam aperture like shown here, and in this case, what they wanted to do was understand how deep drawing of stainless steel alloys of different types, how the residual strains are different along the thickness and also the height of the sample. So what they've done is they came by our beamline with these deep drawn cups that have wall thickness on the order of 2 millimeters, and probably the diameter was probably about a couple inches. And they measured using this diffracted beam aperture what the residual strain was across the thickness and also along the height. And these are some of the plots that they've generated for the hoop strain component. And this is the thickness, the x-axis is the thickness, vertical axis is the strain, and different colors and different markers indicate different positions along the Y. And you can see that the strain is not only very strain gradient, at least the hoop strain is very complicated, not only in the vertical direction, but also thickness-wise direction. And they're all slightly different depending on what type of steel you use because of the mechanisms that are invoked during these deep drawing process. Energy dispersive diffraction technique is a technique that's a little bit different than the technique that we'll be mentioning today. So this technique uses a polychromatic X-ray beam, but essentially uses a similar idea as here, placing a diffracted beam aperture to isolate a particular volume. But now what you're sensitive to is not the angular change induced by strain or induced by strain, but you're now looking at the energy changes and the conditions at different photon energies that satisfy diffraction condition. So in this case here, what we were trying to study here was a shark vertebra that's, as you can imagine, as the shark swims along, it undergoes very complex loading condition. And we wanted to see if there is any crystallographic preferred orientation because of the evolutionary pressure and the physiological pressure applied because of the behavior of the animal. Right, so we're looking at this bone structure that if you'd had a cartoon picture of it, it would look something like this in 3D. And in fact, when you measure it, when we try to measure it with energy dispersive diffraction here, where if you have a detector like this in a horseshoe pattern, looking at different scattering vectors, and if you, for instance, looked at a particular peak, in this case, the C-axis, which is the stiff direction on these that constitutes this material, you see that depending on where you are on this bone structure, there's more prevalent to have C grains with the C axis aligned with detector that's pointed in the horizontal direction versus others in sort of the interior of this carcaniform structure, the vertebrate structure here. Now, as you start to rotate your sample, like I mentioned before, it starts to fill in the pole figure surface or the reciprocal space for surface. And what I'm showing you here, if you have a sample translation and simple rotation, you can get a 2D map with each voxel having pole figures associated with it. So in this case, you have a sample that was cut from a titanium piece that has this classical stringer microstructure or stringer preferred orientation with the C-axis pointing at some direction that it likes to because of the processing path. And if you make a sample that looks something like this, and you interrogate different points on the sample, similar to the EBSD patterns, you can get pole figures for each point on the sample about the preferred orientation that describes a preferred orientation. And with this, of course, if you had these type of information, you can even go further and then do a proper quantitative texture analysis. And you can do this for strain, you can do this for dislocation, peak width, to understand how your material is behaving. Now, if you were to take this one step further and you do rotation and sample and translation with a smaller beam. Now, so this is conceptually very similar to the stitching direct beam tomography. And this has been sort of a very interesting topic that's been in development over the years, including works by John Armour and Stu Stock at APS, and also a lot of work going on in Europe with ESRF and other facilities. And we've invited Henrik Bergdahl from Aarhus University to talk about this very interesting topic and how we extract 3D reciprocal space information for each voxel in a spatial 3D map. What's sort of called as tensor tomography. So I'm very, very excited to hear from him, his take on his work and this field. So if I don't now switch over to the sort of the classical definition of high energy diffraction microscopy, where now you're introducing, you're looking at grains that are grain sizes that are similar to the spot size that you have, and you're still using scattered beam as contrast mechanism. In this case, what's going on is you have very isolated, very sparse pattern because diffraction is very selective. And what you're trying to get is you're trying to get some attributes about individual grains. So far we've been talking about aggregate or average of grain and their attributes. Now we're talking about individual grains. We need to rotate the sample because we're using monochromatic X-rays, and we have to collect diffraction spots. And we do this and we take these diffraction spots and we do reconstruction, what is called indexing, to obtain various attributes. And we've invited 3 different speakers to talk about this, how this technique has been used in a variety of ways, including Dr. Zhang and Paul Shade from Air Force, and Marm Dixit from Oak Ridge National Lab. Here are some attributes that's available from the different variants of high energy diffraction microscopy. And near field HEDM, you can consider that as a non-destructive EBSD technique. And far field HEDM, you don't get a space filling map, but you get the grain center of mass orientation and the strain of those grains. So typically what we can do with these, with the samples, we can interrogate up to about a diameter of 2 millimeters in the XZ plane. And typically we can get a space filling map like so. Here, the colors denote a different orientation in a sample that's about 1 millimeter by 1 millimeter. And we can cycle it, grow a crack, and identify using tomography, direct beam tomography. And also from far field, you can identify what the stresses or strains might be on this sample near the crack front and away from the crack front. Here, I'm plotting the strains or the stresses that's been already converted of these constituent grains as the sample was loaded and cyclically loaded and fracture was starting to happen. Now, we can also do stitching with the HEDM technique to enlarge, for instance, to enlarge the field of view. In this case, what we're looking at is a foam structure that's 5 millimeters wide in 2 directions. So clearly this does not fit in one field of view, which is 2 millimeters wide. So what we can do is we can again use a stitching approach to characterize a structure like this that's very sparse but very large. Okay, and this is and track how the structure changes both in terms of just pure structure-wise and also crystallographic orientation-wise as you compress these things. And this has been demonstrated by our 1ID team and Ashley Spear group at Utah. And also we can go stitching in a different route where you use a smaller beam than the typical beam that we use, which is the 2 millimeter wide beam, and really try to get the intragranular state of material with about a micron type of resolution using a pencil beam here. Okay, so this one we're very excited to have Ashley Bushek from University of Michigan, who's been leading this effort, collaborating with us with Peter Kanashe and Hemant Sharma, and we're very excited to hear about that effort there. So now, all these techniques so far, this HEDM technique and point focus HEDM technique has been sort of pushing the resolution limits to about a micron-ish type of spatial resolution. How we can push that a little further? Well, we can exploit coherence from the new upgraded APS storage ring and use what is called Bragg coherent diffraction imaging, BCDI. And we'll hear more about this from Stefan Hruskovich talk later today. And also, we can also exploit X-ray magnification optics that allows us to magnify real space image. And we're excited to hear about how that is done with Dr. Gustafson's talks later today. Okay. This is so-called this dark field microscopy, and basically this is using the HEXM optics, but in the diffracted BM geometry. Okay. And of course, we want to do this routinely and zoom in and zoom out. So we are really striving for this just-in-time HEDM data analysis using Midas software suites. And Hemant is not here today, so I will probably give a little introduction to what we are thinking about in terms of development pathway. And we also want to deploy some artificial intelligence and machine learning to identify rare events. And Nino Miselli from APS will talk about that effort and how we will deploy these type of new tools to help us guide our experiment and drive our experiments. So as a proof of concept, we've done some work using BCDI and demonstrate the zoom in and zoom out idea. So this, I'm sure, Stefan Hruskovich will talk more about it later today. Just to give you a little snapshot of it, we basically had a substrate, gold substrate, that had about 7,000 grains, illuminated with coherent beam, measured and identified it using far field first, and then measured a particular grain from that illuminated volume using partially coherent beam, the APS beam, the current or APS beam before the dark period, and we were able to reconstruct that structure of that individual grain using this BCDI technique, phase retrieval algorithm, and we were able to measure two Bragg peaks from the same grain, measured at two different locations, two different detector locations, and we are able to reconstruct a similar shape, even though they were measured at two different places of the two different configuration of the detector. So this is a quite exciting development, and we want to make this more streamlined so that this becomes a more routine tool as we zoom in and as we develop this HEXM beamline where we can do zoom in and a zoom out. So that the mesoscale measurement and the nanoscale measurements. So to summarize, so the present day 1ID beamline is home to all these techniques here. And they will be enhanced in the future 20ID beamline with these type of enhancements. For example, in the tomography, typical beam size that we have right now is about 2 millimeters with novel optics, and just the distance of the hutch, we'll be able to attain larger beam sizes, something like 4 or more. In the SAX regime, we'll be able to interrogate something smaller than what we can do now, approximately 1e minus 3 inverse angstrom. WAX, we believe, will be reaching sort of the levels of the high resolution powder diffraction program type of resolution because of the size of our hutch, which I will describe in the later slides, how that hutch looks like. And of course, the scattering tomography or HEDM with stitching, we believe that we can attain now horizontally about 1 micron resolution because of the improvements in the storage ring from the currently about 15 micron resolution horizontally. Of course, some of the new exciting development that will give us the further zoom in techniques, such as BCDI, we'll be able to now interrogate about 10 micron type of grains instead of currently limiting about hundreds of nanometer grain. And then we're going to be deploying TXM techniques that we can currently attain about 500 nanometer resolution down to about hundreds of nanometer resolution. And of course, the increased the number of photons that we deliver, we'll be able to do these rapid measurements a lot faster. Let's skip this slide. So, of course, so now if I switch over to a little bit to our APS upgrade project and how all these techniques that we are hoping to realize will be deployed. One of the main thing that we are working on right now is the HEXM beamline, the high energy X-ray microscope beamline, located at 20 ID. So all the way across on the other side of the APS. And the outer structure has been built for quite some time now, about a year plus. And what it will be home to is we'll be sharing this space, this long beamline space, with the inelastic X-ray scattering beamline and HEXM beamline here, and then activated materials lab that'll be home to that'll house some of the radioactive materials handling, so that we can collaborate further with activated materials community. So this is how the top view looks like. This is the current APS experimental floor. The front end with the 20 IDA. Yep.
I thought you were looking at the notes. Don't bother. Please continue.
Oh, yeah. Sorry. Yeah, so we have the 20 IDA hutch that will be that'll be housing our monochromators and various types of optics. And of course, our beamline is very long. Endpoint here is about 180 meters from the source, which gives us a lot of flexibility in terms of where we place our optics and several variations as to what we can do with beam conditioning to deliver the right beam at this 20 IDE hutch. That will allow us to deliver this highest resolution. And we'll be building this 20 IDD hutch at the end of the experimental floor, similar to 1 IDE, which will give us sort of the highest flux at that location. Okay, so 20 IDE Hutch, 20 IDD Hutch. It'll be similar in dimension as one IDE. It'll be home to 2 different programs. One is the high throughput HEDM technique instrument that is currently at 6 IDD Hutch. We'll be moving there to the front side of the Hutch. That's what we are hoping. And downstream end will be home to this dynamic or fast wax program, where we will have a high load sample manipulation system to house various types of instruments that are built for high energy X-ray techniques, and something that will provide some dynamics, okay, such as AM chambers. So we'll have that program there, and hopefully we'll get this getting built very soon. Construction takes time. One comment about the temporal limit. So we've APS 1ID Hutch 1ID program has done some high dynamic work, like I've indicated before, with the AM chamber, or some of the work that Todd Hofnagel's group did in the past with the dynamic loading, and they were able to measure with about 40 microsecond exposure time reasonable peak signals. So since then, since this period of time, we have 3 times more flux with the improved insertion devices, and also APS-U will be providing 5 to 10 times more additional flux with the sort of the white beam, pink beam mode. Okay. So in theory, we should be able to reach 1 microsecond type of exposures. Now, of course, one of the limiting thing is the detectors, and we're looking at various detector technologies. Some of them now starting to reach this type of resolution. It's not mentioned here, but anyways, these are some of the candidates we're considering to get as close as we can to this 1 microsecond type of temporal resolution. 20 IDE will be a very exciting Hutch. Will be located at about 180 meters from the source, like I mentioned, giving us a lot of flexibility in terms of types of beams that we can provide, and also the sheer size of the Hutch, which is about 20 meters long this way, and then and 10 meters wide this way, and 7 meters tall in the downstream end, and it's staggered this way so that we can actually capture the diffraction rings here without having to build this entire thing like a box. Okay, so that's in progress. So it'll be equipped with various types of beam conditioning systems and detectors and sample manipulation system here. We'll have an overhead structure, support structure to house several detectors, and so that we minimize setup time. And of course, we'll have variety of detectors, starting from near field detector that sits about 5 millimeters from the sample down to about about 15 meters downstream to look at small angle scattering or BCDI type of signals. So couple of things that we've been that is getting delivered, and at least I'm very excited about. The various sample manipulation stages are coming into production. For instance, the high load sample manipulation system that'll be very flexible platform to house various types of load frames or heaters or any equipments that users can think of. That will really take advantage of the high resolution and high temporal and spatial resolution that we can provide with this Hutch. So we have a system that's getting built at the moment. A lot of flexibility here, similar to the MTS table that we have at 1IDE. We have the high resolution sample manipulation system and the D2 detector system, which will be the workhorse detector for a lot of our applications. Those are the single detector far field measurement. But what's unique about this is that the sample manipulation system will be using a large hexapod that'll be able to deliver the degrees of freedom that's necessary for some of these higher resolution techniques, such as dark field microscopy, that needs the rotation axis to be in a particular configuration. So that's quite novel and exciting that we're going to be building this. And the components are getting delivered as we speak, and we're testing them out. The downstream end of where the D2 detector is not just a detector holder, and it'll also use a hexapod. What it'll be is it'll be housing a D2 wax far field HEDM detector on one side, and when it's in use, it'll swing into the diffraction to measure the diffraction cone. And when it's not in use, we can place. It'll have a TXM DFM lens stack that can be in the TXM configuration in the direct beam, or using the hexapod again at the bottom of this structure, so that you can manipulate this TXM lens into the dark field microscopy configuration. This will be quite novel design, and our lead engineer Sunil Bean has been working tirelessly on this. Very excited to see this come to real life and testing it out and using it and providing it for the users. So originally I was going to do a real tour of the 20 IDE hutch, but there was some activity construction going on, so I will have to do with a video. So this is what the hutch outside, if you look out from outside, and if you do a cutaway, that is what is anticipated to look like. What you're seeing here is the D3 detector, and that is the D2 detector stack that I was talking about. And in this case, we have the high load SMS placed in the beam that gives a lot of flexibility in terms of vertical motion and weight that this payload that this thing can carry. Upstream of it, we'll have a beam conditioning system that'll house some of the optics that'll deliver the beam that we want. And of course, more upstream, there'll be more optics that'll deliver the beam that we need. And of course, we have the overhead support structure here that'll be housing our tomography and near field detectors. And perhaps various robots that'll hold other types of detectors that we be using to characterize the sample. And going more downstream, like I mentioned before, our hutches has is staggered like so, like a combination of two volumes, so that we capture sort of one angstrom peaks at 40 keV at the outer periphery of this space here. Right now, the configuration we're talking about, or of this D4, is not a swing arm like this, but a stationary sort of vertical and horizontal translation motion. But nevertheless, we'll be able to interrogate peaks up to the corners of the hutch. And then we briefly went by, but there will be a TXM and SAX detector at the end of the hutch. Okay, so skip this one, and then we'll have a suite of in situ environments. Basically, some quasi-static and moderate temporal resolution experiments designed for those type of experiments. Something like our compact load frame or RF furnace and RAMs that we're developing in collaboration with Paul Shade and Basil with Air Force. Okay. And of course, we are looking for other opportunities to develop in situ environment resources relevant for activated materials lab. And also, we are also looking for other collaborators that might be interested in developing other techniques or other sample environments. Going a little bit on the data management aspect of things, we really need just-in-time data analysis, not just collecting data, diffraction patterns, but really getting maps so that we can make the zoom in and zoom out capability a reality. So what we're working on is we're working with our computation X-ray group and also our neighbors at ALCF to really take advantage of the computing resources and smart algorithms that we'll be developing. The idea being that when we have a tension sample like this and we pull it, we get this raw data, we immediately analyze this data, and we somehow process this data to a virtual Polish crystal. We can maybe even simulate it or identify interesting points in the sample, and then use the zoom in method to investigate these type of hot regions further. And continue this process as we go. So naturally we'll need some help from computers, not only in terms of data processing and identifying what is interesting so that we can make good judgments about these zoom in and zoom out measurements. So like I briefly mentioned, alluded to, we are hoping to work and we're in the process of working with ALCF community to really deploy this data reduction and data analysis pipelines, and really trying to hope that we'll have on-demand computing resources, because this is a little bit different than how typically these high-performance computing architectures or facilities work. These type of facilities, you sort of have to wait for the queue and wait for the computers to free up before you run your work. But I don't think that will be a feasible model for our part, because users and beam time is very precious and we want to have on-demand computing resources. So we're trying to work on that and make this a real thing. And of course, we're getting very fast computers with a lot of flops. So hopefully we can deploy this and make this a tool that users can use. I'm going to skip this slide. So so to summarize, the Materials Physics and Engineering Group will be providing world-leading high-energy X-ray techniques to meet user needs and scientific opportunities. Deploying these techniques will make a lot of these zoom in and zoom out techniques and push the resolution limits further down into the nanometer length scale and really close that length scale gap. I've provided some updates on the HEXM construction today, and I hope that this the talk sets a platform for where we can start talking about more collaboration opportunities and discuss some first experiments and collaboration for how we can reduce this data and use this tool more effectively. So with that, I'd like to thank the audience. Thank you very much for your patience and listening to this talk. And I will open up the floor.
Okay, thank you, June. So the intent of really this workshop is meant to have an open discussion. So I know we have a combination of new users here. So of course, for new users or prospective users, feel free to ask questions. This is exactly what this workshop is for, as well as experienced users that might have questions about the specifics. So we'd really like to open this up. Don't feel shy or bashful. June is at your disposal, if I can say that, to help address some of these questions.
Oh, I'm looking at the chats.
Oh, sorry.
Sorry, yeah, so yeah, it says ISN is in situ nanoprobe. Sorry, I think I said inelastic scattering. My bad.
I see a couple of hands raised, although I'm sorry, I'm not. Oh, there we go.
Yeah.
Omlin. There we go. Feel free to unmute yourself and ask a question.
Thanks. Hey, June, thanks. Excellent. Great talk. I have a few questions, but I'm going to go with one first. That you mentioned a 1 micron resolution on tomography, right?
Yes.
I was wondering, what is the limiting factor there?
the main thing is the pixel size on the detectors that we have. That'll be the main thing. Peter can probably give you more lengthy explanation as to where that comes from, but yes, about a 1, yes, from the detector pixel size.
Okay, thanks.
You mentioned a couple of questions. Did you have a second one?
I'm gonna hold off for now. Thanks.
Okay, great. Let's move to Todd.
Yeah, great. Very nice talk, June. I guess a couple of things. So
Yep.
this is not necessarily like for right now, but for planning purposes, it would be nice to have some sort of timeline about when the various capabilities we think will be ready. I don't know how hard that is to project at this point. But thinking of when the APS reopens, when the array of capabilities you outlined is amazing, right? But just knowing sort of when these things will be able to come online would be helpful. And then I guess the question that I had was, and maybe you mentioned this in your talk and I missed it, but some of these very long distances, I think, give you interesting possibilities to do both imaging and diffraction simultaneously. There's issues there with what the scattering volume is and the imaging resolution and all that sort of thing. But I'm just wondering if that's something you've thought about, is putting an imaging detector in the beam simultaneously while trying to look at diffraction.
Yes. So the first question, I think John has some. Later today, John will give you some guideline as to how this might look like. Sorry, I'm putting you on the spot there, John. I'm personally thinking it'll take many, many months to do the commissioning of the beamline. And then for the general users to actually use these tools, it'll be optimistically 2025, but this is very personal thing. It's not official. I'm not in a position to make any official statements. But as you know from our HEDM development, it took us some years to actually make it a user program. Like, for example, the RAMS 3 combined with HEDM, so that'll be a good benchmark, I think. Reasonable benchmark, maybe. With regards to the imaging and the diffraction question, so the idea is that we'll do these measurements not necessarily simultaneously, but maybe or concurrently, but one after the other, if possible. We'd have to see how things play out. Of course, I mean, some of these more novel techniques where the direct beam is unobstructed, or maybe we can also do them concurrently. But yes, I mean, we'll continue to.
So concurrently is, my interest in things that are dynamic, right? So
yes,
so concurrently is very interesting from that point of view.
Yes, we do. So, I mean, there are a couple of challenges there. I mean, one the main thing would be sort of exposure time matching. So one thing that we often do at our beamline, as you know, is SAX-WAX. And at the moment, we do them concurrently. One of the unfortunate thing is that because how things scatter at wax and the SAX regime is different, sometimes we get nice signal in wax and then SAX signal not so good, or vice versa. So we have to sometimes make some compromises. But I think there will be some, if we can sort of match that type of exposure time issues and come up with a nice material problem, I think it'll be a very nice thing we can pursue. And we keep wanting to pursue that, but the material has to cooperate.
Right.
Yeah.
Great, thank you.
Yep.
John, did you have a question?
I was going to just comment further on that. And I think, I think the timeline of what we're going to put out there for users, we'll give general answers, but not in great specificity at this point, but as you can understand. But I think what June said is in the right ballpark. in terms of that diffraction and imaging, I think the fundamental issue, as you know, is different volumes that you usually want, right? With imaging, you want to see a big sample, and diffraction typically smaller. But if you can get away with those, that mismatch, and you can deal with the dynamic range, there's nothing fundamentally that would limit you from doing that in either the D or the E station. You know, you might have to make some compromises, but as you can see from June's slides, like we'll have a tomography detector and you can either have the D2 or D3 detector at some distance away and you can get half a cone. You know, it's going to be contaminated a little bit potentially by the imaging. We could try to put some shielding in, but it's possible. So we always expect people like you to push our limits. So
Always happy to push your buttons, John.
So not to be more restrictive on what John and June say, but they've already been a little careful how they answer questions. I guess they know that this is being recorded here. So I guess with that, Sven, over to you.
Thanks, Mike. And June, great talk. It was good to see the current plan of the upcoming beamline. It was exciting. I have two simple hardware questions, I suppose. Is there a current choice for a far field HEDM detector? Is it a GE or potentially something with a higher dynamic range?
Interesting question. So we really have to we have a couple constraints. One is we want to satisfy users and get good dynamic range, fast, everything. But then we also have some budgetary pressures and constraints. So we have to maneuver that a little bit. That being said, so our general idea would be we're considering something like a G detector or a CMOS type detector for everyday use. Sort of the, I think I put it in the slide somewhere, sort of in the tens of hertz frame, FPS frames per, tens frames per second type of thing. So there are some detectors out there mainly developed for medical imaging that can reach that kind of frame rates with very good resolution. Let's say about 100 micron type of pixel sizes. So that'll be our workhorse. And then of course, as we are doing right now, we are pursuing, as we're doing right now with this Pilatus detector that we have, we're pursuing some other, these high dynamic range, perhaps high dynamic range. It is photon counting detectors that have theoretically maybe higher dynamic range and also much faster frame rates. So that I think we cannot do it alone with HEXM only. We'd have to team up with other beamlines and whatnot, and we are looking into that option as well. We'll see what happens. We'll let you know.
Perfect. Thank you, June.
Yep.
One other quick question on the lenses that you are using for the transmission microscopy as well as the dark field microscopy. I believe I heard you say that they'd be used for 40 keV. Is that correct? Or
well,
is that unknown?
Well, I mean, we aren't necessarily going to be bound to the energy per se. Of course, working at slightly lower energy than say at 130 keV has some advantages. But in theory, we should be flexible enough to work at different energies.
Good to know. Thank you.
Yep.
Great talk again.
Thank you.
So maybe in the spirit of also making this open to new prospective users, June, could you maybe say a few words about, from your experience, what works well for new users to get into the door? I guess the steps before they actually show up for beam time, or anything to lower the energy barrier to start up a new user group.
Very interesting question. I personally, my recommendation is talk to the beamline staff early than later. So if you have an idea, please talk to us sooner than later, because it gives us a lot of time to sort of brainstorm and talk about what are the options, what scientific problem you're asking about, and what kind of probe is appropriate. And also, doing some feasibility measurements if you can. And we do provide that type of support, as a lot of our experienced users know, we do offer our users, if you have samples already, we can do some feasibility measurements, because one of the challenging things with these diffraction techniques is really matching your sample to the technique that you are asking for. So for instance, HEDM technique, you're sort of bound by the grain size that your sample has and how nicely it scatters. So, we do a lot of those feasibility measurements. We try to do a lot of those. So that'll be two things. So one is talking to us early and discussing early, and I hope this opens more opportunities for people to talk to us, particularly during dark times. And feasibility, I'd say, we don't have beam right now, but when the beam comes back, we will happily do some feasibility measurements and evaluate how things look like. I think John has his hand up.
Yeah, just to put a finer point on that, I mean, I think June and other beamline scientists have been doing kind of off the books feasibility measurements with users for many years to do just that. To often you can see a lot in an hour. Part of we've discussed and thought about having a more formal kind of mail-in program for that. There's an energy barrier to that, and and frankly, we haven't really had the capacity to do that in other things. But one of the philosophies behind the design of the beamlines now is at both 20 ID-D, the station before E, where we have the high throughput instrument going in, and at 1 ID-C, before the 1 ID-E kind of main station, we're trying to have more fixed setups where people can more readily do kind of, I don't want to necessarily call it mail-in, but certainly feasibility studies, and it might move to mail-in, it depends on. So that's certainly a key area, not only for getting more samples through, but getting samples, screened early.
Great, thanks, John and June. Other questions? Okay, considering we had we had a cancellation on one of the talks, we're a little bit early in terms of the schedule right now. I believe we have a break scheduled until 10:45 Central Time. So with that, I think we're pretty close to being on schedule. We'll take a 15-minute break. And then at that point, we're hoping Marm Dixit, and I'm looking at, it looks like Marm's has joined us as well. Marm Dixit, one of our co-organizers, he'll be giving a talk at 10:45 Central. So with that, I want to thank everybody, and we'll see you guys in a few minutes. I am going to stop the recording now, and then we'll start back up at 10:45. Thanks, everybody.
Thank you.
Thank you.
Oh, started recording already.
Oh,
Very good.
fancy.
Very good. Okay, so I think we can get started again. Can you guys hear me, Marm and
Yes, sir.
everyone? Okay, so I'd like to get the second session started. Our first speaker for the second session is Marm Dixit from Oak Ridge National Lab. Dr. Dixit is from Vanderbilt or Princeton now? Do you associate with Princeton or Vanderbilt?
No, Vanderbilt.
Okay. So he received his PhD from Vanderbilt, studying batteries, interesting material system associated with batteries. And he's a recent recipient of the 2023 Rosalind Franklin Young Investigator Award, very prestigious. And he's going to talk about how we can use high-energy X-ray microscopy to study battery material systems and his perspective, present his perspective. So thank you for agreeing to speak to us, speak about this topic, and the floor is yours.
Thanks, June. Thanks for the kind introduction. And so June said, I am at the Imaging and Solid State Battery Group at the Oak Ridge National Lab. The work I'm going to show you today involves stuff that I did during my PhD. At Vanderbilt, the group has since then moved on to Princeton with Kelsey. Wahid was the grad student who worked with me. These very fine folks here that you see are the ones who actually did all the work. I was just hanging off of them, trying to understand what was happening. Then since then, I have joined the Imaging and Solid State Battery Group and at the Oak Ridge National Lab. We also had some collaborators at Purdue who helped us with modeling for this work. And so just a quick introduction for the crowd here. Conventional lithium-ion batteries that we use in our cell phones and laptops and recent cars have a liquid electrolyte in them. And the problem with that is you can only have so much energy density. And that means you can only drive that car so long, 300 miles or so. What you want to do is engineer batteries that can last for 500 miles, essentially extending the energy density. And to do that, we need to really use metallic anodes, lithium metal, for example. But the issue with conventional liquid electrolyte is that these lithium metal forms these filaments, and we get shorting and thermal runaway and a lot of degradation that happens when you use conventional lithium ion electrolytes with lithium metal. And so we wanted to, so in order to make this work, we have to move to a solid electrolyte. And the idea there is that the solid material has a better propensity to mitigate these filament formation and all the bad things that happen when lithium reacts with conventional liquid electrolytes. And so that is what we are studying. We are investigating these separator materials, which are essentially ionic conductors and electronic blockers that goes inside a battery that shuttle ions back and forth. Within the solid state battery itself, there are a lot of challenges that we need to understand. And what we are going to focus here specifically is the thermo-mechanical failure of the solid electrolyte. The other challenges that we face with understanding what is happening with these solid state batteries is that the phenomena of interest generally occurring in regions that are relatively inaccessible using conventional characterization techniques. And so it becomes really hard. So that's where I've used a lot of synchrotron resources with real and reciprocal space imaging to understand what exactly contributes to these bottlenecks and how these failure occurs in solid state batteries. And so we are trying to ask three major questions with solid electrolyte failure. The first question is what happens? And we can kind of sort of answer this with electrochemical approaches that we use. We can also ask the question how it happens, and that is something that we kind of sort of answer with imaging, so we can see the progression of how things fail as we cycle the battery. But the toughest question we've so far asked is why it happens, and this is a tough one, and we don't really know the answer to it. And so just a quick rundown of what happens. And so you take a material like these materials are garnet type lithium ion conductors. It's a lithium lanthanum zirconium oxide. And you solid state synthesize them, you make them into pellets, you sinter them. You put lithium on both sides and you try and cycle them at increasingly higher currents. And eventually what happens is that lithium filaments form and they push through the electrolyte thickness, and you essentially short a cell. And for the battery scientist, we essentially look at it from polarization profile. So you can see this voltage in the black curve, it is kind of going up as you increase the current, and that is consistent with Ohm's law, where if you increase the current at the same resistance, the voltage increases. But then if you see that suddenly these things go to zero, that essentially means the cell gets shorted, and you have a lithium filament or lithium dendrite poking through the thickness of the electrolyte and punching through and shorting the cell. And so we are interested, so that now we know what happens. The question of how it happens, it really depends on what kind of solid electrolyte material you are working with. But using some synchrotron imaging methods, we've been able to track the evolution of cracks and filament formation within these solid electrolyte materials, and we are able to hypothesize what is the mechanism of how these things happen. And so with thiophosphates, these are softer materials. Sulfides, we see that this crack sort of forms at the interface, and then you form this vertical crack through the bulk, and then that gets expanded more and more. With garnet-like materials, we see that we have deposition in the bulk of the material, and not something that is more interfaced to. The real Pandora's box, like I said, is why it happens. We have a lot of different people in the field that have their own theories of why it happens. So we have a lot of folks that say the microstructure is what drives the failure. There's a bunch of people who say the grain boundaries is what drives the failure. A lot of people are focused on the interface, where they say that the interface between the solid electrolyte and the lithium metal is what is the main driver of failure. And there are the folks who say that it is just the operating conditions, the pressure and the temperature that really drive what is happening in terms of instabilities in these materials. And so the real question we are asking, right? So what you see here is a grain map for a garnet type solid electrolyte. These grains don't come labeled with burglar symbols like this, like they do in movies. So we don't know what grain causes it. And so I like to think of failure in these solid electrolytes as a rare event, and it is very challenging to identify which individual grain is the one that is causing it. And so this was a problem that we were facing, and that's where high energy diffraction microscopy came in, where we could track individual grains of these solid electrolytes in bulk. And so this is one ID. I'm sure a lot of you are familiar with this. We have our sample. I'm going to zoom in here. We have our sample right here. Let's see. We have our sample somewhere in the middle of the screen there. A tiny cell that we make, which has like a garnet electrolyte pellet around 1 millimeter in diameter. And we've connected it to a potentiostat that allows it to cycle in situ, and we can charge and discharge this battery. And so what we are imaging is around a 2 millimeter pellet with a 1.2 millimeter thickness, and your standard far field diffraction microscopy geometry. And so I'm preaching to the choir here, but essentially we were able to, if you get things just right in terms of X-ray energies, lattice spacing, grain sizes, and the sample size, you can essentially track the grain center of masses as well as the lattice strain as you cycle these batteries. And so what we essentially did was replicate the lab experiments that we do in charging and discharging a battery at the beamline in situ, where we see clearly a very consistent behavior, where we see flat polarization profiles initially, and then these wonky profiles that kind of sort of says that, well, we have shorted our electrolyte. And we also see this with electrochemical impedance spectroscopy. And so this is one more measure that electrochemically we can show that we have shorted the cell. And so what we are doing here in terms of characterization is we are doing far-field diffraction microscopy of the pellet at each of these individual steps. We also are carrying out tomography at the same time step. So at each state we have a full far-field diffraction microscopy map as well as a tomography scan at each of these time steps. And that is what we want to evaluate how these things evolve over time. And so what you are seeing here is the grain map from the solid electrolyte garnet materials. What was surprising to us, and so we have quite a bit of charge passed before we failed the cell. And what was surprising to us was that the average hydrostatic stress does not really change. So for these 230 space group, 220 space group, we found around 30,000 grains within a pellet. And on average, that hydrostatic stress was basically zero. And that to us was very surprising. What was also interesting was that the maximum and minima showed some deviations. And so there were some fluctuations that were happening at the maxima and minima. And so led us to think that it's the degradation and the failure mechanisms that are occurring in the solid electrolytes are not linked with the bulk material, but probably they are linked with something that has to do with these minimum and maxima phases regions. And so since we had a corresponding tomography scan, we were able to geographically locate the regions of these hotspots and cold spots within the grain maps to a physical location in the tomography scans. And so in solid electrolyte world, it is understood that if you see a change in porosity in the tomography scans, that is consistent with formation of cracks or formation of lithium filaments where you deposit lithium, because within the bulk electrolyte there is not enough contrast to distinguish between pores and lithium metal. So any change in the X-ray transparent region or the less absorbing region that we see, we essentially think that as a crack or lithium filament. And so if you see, we have two regions here. One that was a region that is near the bulk, so which was the zero average region, and one where we had a maxima or minima. And so we can clearly see that between the failed and the pristine sample, this region showed essentially no change in porosity, but the region which was a hotspot or a cold spot that we investigated was